So hello again. Tonight we're going to talk about modulated gravitational wave generator, or last week we talked about gravity waves of a specific wavelength and frequency, very, very long, ridiculously long wavelength gravity waves. And we were at the end of the session after the presentation sort of poking around, how would you generate gravity waves? And we came up with a Newton's cradle approach with giant metallic balls in an evacuated room. And so I said, there's something to be thought about there. So that's literally where I started with this is how would we generate gravity waves? And are we already generating gravity waves and just aren't realizing it? In radio astronomy, when people are talking about when was our first broadcast to space, and they're thinking about something we did at Arecibo deliberately, where we want to send a signal out there that some other intelligent species can decode. And then was pointed out, we've been broadcasting since the the late 1930s, officially broadcasting. Well, that stuff at the particular frequency leaked off of the Earth into space. So that's been traveling at the speed of light ever since the late 1930s. So we've been sending a signal out for a long time. Well, the same thing seems to hold true for gravity waves. We've been making gravity waves for a really long time and just never realized it. So we'll get into that. So the prior presentation was on ridiculously long wavelength or ridiculously low frequency, RLF, gravity waves as part of a gravitational wave background, and how we're now starting to look for such gravity waves indirectly by snapping pictures of the polarized cosmic microwave background and then seeing if anything ripples through it. So if you take a sort of a repeated image of the microwave background and then you see like the pixels shift in kind of a line going across there, that would be a gravity wave distorting the space-time between you, the observer, and the signal you're getting from the cosmic microwave background. So that's how they're looking for these ridiculously long wavelength gravity waves. Following that discussion, we started talking about how you would generate them. And we got into then, well, if you can generate them, then you can modulate them. That just means you can apply information to this signal, the carrier, and we can put data and voice and video on there. So tonight we'll go over postulations of how you might modulate gravity waves. So first, a brief overview of what are gravity waves and how are they currently being detected. Big Al, Albert Einstein, was the guy who said, with all these extreme gravitational effects of black holes and such, that ought to actually expand and contract or ripple space-time. And so he was the first guy who said, I think there ought to be gravity waves, but it wasn't until much later, like I think about 17 years ago, that we started thinking about maybe we ought to build some observatories that can detect these theoretical gravity waves. And we'll start at a certain design, and that design is embodied in 3 observatories called LIGO, VIRGO, and KAGRA. LIGO, there's 2 in the US, VIRGO is in Europe, and KAGRA is in Japan. And they fire a laser beam off. They run it through a 90-degree beam splitter. One beam goes down through an evacuated column inside of an underground cement tunnel, and the other one goes off 90 degrees like an L, the other direction. And at the end of the tunnels, there's mirrors, and the mirrors reflect the beam back. And if they get the precise distance down both tunnels from the beam splitter to be precisely equal, then they'll cancel each other. And if they cancel each other, they can detect that in their detector because it goes from a beam split to a beam merge. They detect it. Everything's canceled. Must not be any gravity wave. But if down the mile plus long length of these tubes, they get stretched, they get rippled in space-time by gravity waves to a fraction of the diameter of the distance of a proton inside of an atom, that was a gravity wave. And initially they weren't detecting gravity waves, and so they had to refine the instruments and use a higher power laser and things like that. So they've improved it and now they can detect maybe 2 or 3 gravity waves per week, but they're from very large things as they close on each other in orbit very rapidly and then merge. We've also started working on orbiting satellites. So if you put 3 satellites in kind of a corkscrew orbit with the Earth, and they use lasers to accurately separate the satellites, then inside the individual satellites, they can have little blocks of metal that sit there in the zero gravity of space. And as they rotate around, if anything ripples through there as a gravity wave, the little block will move a very, very tiny amount. And that's how they detect gravity waves in space. But they're moving from the first interferometers, the space-based ones, and it doesn't go up a lot. They can't get like really long gravity waves. They can get longer, lower amplitude, but not really long ones. So the next thing up from that was timing of pulsars. So they'll pick maybe 20 pulsars spread around the sky. And these are what they call millisecond pulsars. So they're pulsing. They're neutron stars that are spinning very rapidly. And we get, from Earth, we detect radio pulses from them. Not artificial pulses. These are natural. We time those pulses down to a, very, very fine degree, down to far less than single nanoseconds. And if the timing changes across the array of pulsars, we can actually say that was because there was a ripple in space-time which expanded and contracted due to a gravity wave moving through there. So after, I think it took them 17 years before they got their first confirmation, and then about 21 years before they had like the appropriate amount of observations that they could go, yep, we got gravity waves. And that's the International Pulsar Timing Array. Multiple countries doing this. And in the US, it's called NanoGrav. They could detect, let's say, light year wavelength long gravity waves. And now they want to detect even longer ones because they've kind of put the assumption out there that they're much like there is a cosmic microwave background, there is also a cosmic gravity wave background. But the wavelengths are so long that not even the pulsar timing arrays can properly record them. So they have to do this indirect imaging of the microwave background and see the ripple through there to see these very long gravity waves. And right now they've got 2 observatories that they're near to functioning, and they've got a total of 21 of those observatories that they're going to be producing. So look forward to them detecting and confirming very long gravity waves in the next few years. But why are we looking at gravity waves? Well, gravity waves, like certain electromagnetic spectrum wavelengths, pass through pretty much anything. Gravity waves don't just pass through things, they ripple things. They will pass through galaxies and stars and moons, Earth. They pass through people and you never even know what happened because it's such a small scale and it's just expanding and contracting the fabric of space-time. And there's no actual effect. Nothing, explodes, blows up, or dies of cancer or anything like that. It's just, that's space-time for you. But given that it'll pass through anything going on for many light years distance, that would be a great way to send voice and data and video across deep space where it doesn't get distorted by things in the electromagnetic spectrum. So great, let's just go out there and do gravity wave-based communication. But we got a couple of problems first. The first one is, how do we receive these very long gravity waves as a signal source? And then how do we demodulate the data from the received signal? That's number one. Let's say you can decode it. How do you send it? Now you have to have an ability to very precisely generate specific wavelength, specific energy level gravity waves. And that's where we get the concept of modulated gravity waves. Can you produce a gravity wave as a carrier? And then can you adjust that carrier to encode data on it so you can now have a modulated gravity wave? It doesn't matter whether we start out with the really long gravity waves or not. It's just we need to find a way to decode gravity waves if there's a signal modulated onto them and then to do it ourselves, transmit gravity waves with a modulated signal. Once we get these two things, receiving demodulating and then sending modulated gravity waves, it will be as far-reaching an advancement in human deep space communication as coming up with modulation of the electromagnetic spectrum was above smoke signals. So how would we generate gravity waves? Well, we don't necessarily have to move around white dwarf stars or neutron stars or black holes. We just need the effect. So we can currently make things that weigh a lot, big heavy masses. And we can generally move them pretty quickly, but not light speed. But do we need that? What we really need to do is to rapidly accelerate something that weighs a lot and then rapidly decelerate or dampen or dissipate that energy. And we were thinking about a Newton's cradle where you have 3 giant multi-ton iron wrecking balls that you lift up one and it smacks into the stationary 2, and then the one on the outside swings out, smacks back into it. And we were thinking every one of those impacts would be a gravity wave. Well, as it turns out, we're not quite right. It's the movement of the mass through space that is the first gravity wave. And then the collision, the abrupt stop, is another gravity wave. So just the movement of huge masses through space-time generates a particular kind of gravity wave. And then when that mass comes into a collision or an abrupt stop, that's another kind of gravity wave. So the faster we get these gravity waves moving, we get a different frequency of the waves. As they smack harder into one another, we get greater amplitude or signal strength. And then when it starts occurring and when it cycles is the phase of that gravity wave signal. So here's our superscalar classic. The picture is of a Newton's cradle. And you can see that one of the balls has been pulled back, and it's actually a GIF image video, and it will smack into the others. But Zoom's background PowerPoint doesn't support animation, so I can't show that. But there's a link at the end that you can go to Newton's cradle, and there's the video you can watch. But you lift one of the balls up, and that energy that you apply to it to lift it up puts potential energy into the ball. And if you just hold it there, it has a certain amount of potential energy. And then when you let go of it, the potential energy gets converted to kinetic energy, and then it smacks into the stationary balls, which have potential energy, their inertia. It transfers momentum into them, and it goes from ball to ball to ball to ball, going from potential to kinetic, until it gets to the one on the end, and it has no choice. It's going to convert its potential into kinetic, swing out, and then come back and hit the stationary ones again, and you're going to get the classic clackety, 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 clackety. So Newton's cradle. So if we scaled this thing up and we had giant metallic balls that were tons each, and we had them on cables that were very lightweight compared to the weight of the ball, and we could adjust the height of them, then we could adjust the swing angle and therefore the frequency and the amplitude of the collisions. But like I said, you don't really need the collision. You just need the effect from it. Now, how will we lift these balls and let them go in a precise manner? Electromagnets. So electromagnet grabs hold of the outer ball, drags it up on a chain, and then you turn the magnet off and down it comes. Now, we don't need 5 balls. A classic Newton's cradle would have 5 balls in it, but 3 might be sufficient. If we build it big enough, then the LIGO gravity wave detector might detect it. It's not a matter of the wavelength, it's a matter of the amplitude. We're not really doing much in the way of controlling the gravity wave, so there's no ability to really modulate data onto it. So as I was saying, the collision itself is not necessary. Just accelerating and decelerating mass through space-time will produce a gravity wave, maybe not a massive one, maybe not a long-lived one. So as you have 2 high-mass celestial objects orbiting one another, that's a gravity wave. And at the point where they collide, that's actually another kind of gravity wave that dissipates. And if you've ever heard the mapping of a gravity wave to sound, that you hear, that's literally the gravity wave until the two things collide, and then you lose and it stops. So what we're looking for is, how do I move a large mass, accelerate it quickly, and then stop it? And that would generate a gravity wave. So we need to create a massive differential in applied momentum. Not the collision itself, just the application and removal of momentum. How do we want to modulate this thing? Well, if we change because it's just kind of a sine wave, that's gravity waves like electromagnetic spectrum waves, they're just waveforms. The taller the peaks and valleys, that's the amplitude. The wavelength is the distance between the peaks and the valleys, or troughs. The frequency is the quantity of peaks or valleys per second. And then where the next peak starts or ends, that's the phase. So we can adjust all these things to modulate data onto the gravity wave. So the various forms of modulating a wave, modulating a carrier, is amplitude, frequency, phase, or something called quadrature. Now, when we do quadrature modulation, we're lumping together amplitude and frequency and phase, and you're actually transmitting more than one, like 1 or 0, more than one bit in a single wave time. You might be transferring 4, 8, or 16. If you remember those old dial-up 56 kilobit modems, they actually had what is known as trellis encoding, and they could transfer 16 bits of data in one passing of the wave. So as I said, what's actually required is the rapid acceleration and deceleration of a big mass. Not necessarily huge velocities. It doesn't have to go light speed. It just has to move fast relative to its mass. We need to do so in an evacuated structure so there's no air resistance, or if there's a collision, it doesn't make a lot of noise. We can do these things. Making big metal things is easy. There's no cargo to be carried on these balls. It's just the ball itself is its own cargo. But what we actually need is a precise digital control over how much this mass moves, when it starts moving, when it stops moving, and how fast it moves. And that's something called momentum. And momentum is mass times velocity. Now I'm going to look at this from a non-speed of light, non-relativistic point of view, because when you get up to light speed level things, the relativistic characteristics of it change from this simple Newtonian definition of momentum. Down at lower speeds, less than relativistic, photons' energy and mass are kind of all translatable into one another. So you can either say, I've got a photon, it's got a certain energy, therefore I can calculate its inherent momentum as a mass. Even though a photon at rest is massless, a photon in motion has momentum, and that can be mapped onto mass. So we'd like to be able to increase the velocity and then decrease it. And the best way to increase the velocity of something like a photon is to create the photon, to instantiate the photon. It goes from 0 to speed of light in a small fraction of a second. Attoseconds, not nanoseconds, not picoseconds, not femtoseconds, but attoseconds. Very, very small period of time. So we can get a photon moving quickly. But photons have very minuscule mass per photon. So we would need to create lots of them and then abruptly stop them. How do you abruptly stop a photon? Make it collide at 90 degrees to a reflector. So it comes to an abrupt, obtuse stop. So now you can accelerate something and rapidly decelerate it based upon photons. But you need a lot of them. So the thing that I've always described it as, it's something called radiation reflection pressure. As your photons get closer and closer to ultraviolet, shorter and shorter wavelengths, higher frequencies, they have inherent to them greater energy. They can carry greater momentum. The number of photons you produce is your flux, or your photon density. So if you have a small amount that you're transferring with one photon, but if you can transfer many billions of photons, now you can collectively say there's more flux, there's more momentum in that. When it collides with the reflector, you need to very rapidly dissipate the reflection heat that you'll get from an obtuse reflection. So behind the reflector, you need some kind of a, maybe not cryogenically chilled, but cooled to remove the heat. But you could also put a piezoelectric material behind the reflector ahead of some cooling barrier to actually generate electricity from it and then put that back in the system. It's kind of like regenerative braking in an electric car. You went to all the trouble to create this. It smacks the reflector, generates some heat, take the heat, convert it to piezoelectric energy, take that back as voltage. But the reflector is kind of a flat panel. If you want to project the gravity wave in a specific direction, you have to be able to move that reflector panel in 3 dimensions, be able to send the signal. And you need a way of rapidly switching the power on and off of your emitters, your photon producers. And for the people that want the math, here's your math in one slide. Just as an example, the particular LED that I chose was a 100 watt royal blue, which is 440 nanometers. I've got the wavelength, speed of light, the frequency, because you need both frequency and wavelength to do these calculations. Planck's constant, how much energy you would get per photon in joules, and then the mapping that 1 watt, that's the normal W watt, is 1 joule per second. Oh, look, he spelled joule wrong. But I spelled it right in the previous line. So if I have a 100 watt LED, I need to actually put in 119 watts because there's some inefficiencies. There's some heat that'll get generated that we have to dissipate off. If I've got 100 watts going into this thing, how many photons is that going to be producing? Well, turns out it's 2.22 times 10 to the 19th photons per second. So now that we know how many photons we've got, we know the energy per photon, we can calculate momentum per photon, and we can come away with that as Newton meters seconds, which is kilograms meters seconds. And we have a number for that. It's very, very small. It's times 10 to the minus 26. But remember, that's per photon, and we have 10 to the plus 19th photons. So we're a little short of it coming up to be like 1. So how much do we produce per device? Well, times 10 to the minus 7 Newton meters seconds. How much area are we producing these photons over? And it turns out it's 44 millimeters by 44 millimeters, or 1,936 square millimeters, or 1.836 times 10 to the minus 3rd meters squared. That should be meters squared. Well, actually it is. Yeah, it should be meters squared. So how much would I need if I wanted a 1-ton force? If you're doing it this way, then all you have to do is just multiply it up, scale it up. 1 ton of radiation reflection force is 1.25 times 10 to the plus 16 devices. That's a lot of LED. And it would consume 1.49 times 10 to the plus 9 gigawatts. That's way too big. And the area it would take, if you take all these LEDs and you sort of gather them into one giant area, it would take 2.43 times 10 to the 7th square kilometers. So this is obviously, the math works, but the reality doesn't. Of course, it also presumes that the reflector is 100% reflective and that all the photons hit the reflector precisely at 90 degrees. So focusing on just increasing the momentum doesn't get you to someplace practical, but the math does work. There is a difference in physics between force and pressure. Force is something you can cook up and create momentum from. Pressure is the application of that over a square area. And the way to increase pressure, you can either increase the force you're applying, or you can reduce the square area over which you're applying it. Think of it as, if you want to go walking on the snow, you wear snowshoes. Snowshoes are just a webbing that distributes your weight over a larger area so that your foot doesn't go into the snow. Same sort of thing. If we reduce the area of where our photons are concentrated to a very small amount. Now I'm producing more over a smaller area. I'm increasing the radiation reflection pressure of my light source. Think of it as, instead of me turning a beam of light on and just bathing an area, what I want to do is narrow that flux down to a small area and smack it rather than just making it glow. So it might be better if we increase the flux, increase the photon density over square area to a smaller area, and therefore we can reduce the number of emitters, and now we get a smack on the reflector, not a push of the reflector. Because push requiring too many emitters, too much power. There are more expensive cool white LEDs out there that will dissipate more than 100 watts. 200 watts, 300 watts, 500 watts, they're all reasonably priced. By reasonably, around the $50 or less per emitter. And you can actually, they make them so they can be packed tighter together so that you can get them in these 750 or 800 watt level. So I just picked as an example, instead of 100 watts in particular narrow wavelength, I said, why don't we go for the bright white 500 watts? And that package is 82 millimeters by 82 millimeters. But instead of just being one wavelength, small amount of narrowed energy, it's actually bright white, which is lots of different frequencies of light, each producing their own amount of energy per photon. But since I don't have the emission curve, I can't tell how much of the total output comes out at what wavelength. So I'd like to do the math, but I don't have the numbers from the chip manufacturer. But this is essentially how you do it: is you reduce the wavelength and increase the frequency. So if you can get to shorter wavelength, farther from infrared, basically, more efficient, if you can get them to produce more watts of photons out versus watts of power in. As an example, the LIGO laser, the laser that is used at LIGO, the beam is only 5.3 centimeters or 2 inches, and it's only 60 watts. Remember, I was talking about LEDs that were 500 watts. This is only 60, and it's only 2 inches in diameter. That beam moved a mirror. So they switched on that beam, that 60 watt infrared, not even ultraviolet, infrared beam, and the radiation reflection pressure hit the mirror. The mirror is 40 kilograms or 88 pounds. The mirror swung simply by the light beam smacking the mirror. It was only nanometers that it moved it, but still, that's a beam of light that's only 2 inches in diameter hitting a mirror and making it move. Now, the mirror is in a vacuum, so it was easily moved. Infrared photons have less energy than ultraviolet photons. So if I can find out what that spectral curve is for that 500 watt LED, then I can do the math and come up with the number. But 500 watts versus 100 watts is far more photons, 5 times more roughly, a little less than that heat transfer. Far more photons coming out over a small square area, so I can improve the amount of smack that I deliver to the reflector. And as I was saying, if I just turn the beam on, that's kind of a push, a shove. Whereas if I turn the beam on and then turn it off rapidly and just apply the energy, it's a smack. Here's an analogous approach. If you take your hand and you close your fingers together and you extend your arm palm down onto the surface of water, and you just stick your hand in just enough to break the surface tension, and then you pull your hand up, you might have a small amount of short-lived ripples on the water. But if you take your fist and you bundle it up and you turn it downward and you use all your force to smack your fist into the surface of the water, and then you bring your fist back up just after it breaks the surface, you have a smaller area with greater momentum. The result is greater pressure and deeper or greater amplitude, longer lasting ripples. And that's what we want to do with our gravitational wave event. Is we want to turn up the power, make it hit, doesn't have to last but a small fraction of a second. So smaller devices, more wattage, shorter duration. It could even be in that, picosecond or attosecond range of how long we have to deliver the hit. So even less energy. So if we do this very short-lived smack, over time, the smack becomes the peak of the wave, and then we let it decline down, and then we smack it again, and we're creating a carrier. So how often you smack it is the peaks of the waveform. The required power will be less. The amplitude is likely not to be huge, but it's under digital control, which means we can modulate it. But people might think, well, if LIGO is using lasers, why don't we use lasers instead of LEDs? And well, lasers have some benefits. They have something called monochromatic light. So all of the wavelength is predominantly singular. So it comes out at a specific wavelength and frequency. And lasers emit what is known as coherent light or coherent photons, where the photons rattle back and forth between the reflectors. And when they achieve a threshold, they all come out at the same time. So all the photons are hitting at the same time. So you get a collective smack. That would be good. But there's downsides to the lasers. They're more expensive. And for the same amount of output, like if I wanted a 500-watt laser, it would be enormous. And it would probably not be solid state. It would probably be a gas laser, like helium neon or something of that nature, or xenon. Big, expensive, large diameter, that's not going to fit what we need. But it's easier to make LEDs, these circuit onboard or COB and surface mount device, SMD, light emitting diodes or LEDs. Up in the picture there, you can see this is one of the 500-watt ones. And you can see little dots there. All the little dots within the green area, those are individual 1-watt LEDs, all those little green dots. Lots of them there. About 500 of them. They can change the packaging to make it more back end and less side, to make it over a smaller area. And they can even, on the back of them, put what is known as Seebeck stages. They will take the waste heat and convert that into electricity. So you're converting some of the electricity that you generated, produced heat, take the heat, produce electricity, and then when it hits the reflector, some of the shock of it hitting the reflector, use piezoelectrics to convert that into electricity. So whatever energy it took you to generate the smack, you're actually getting back maybe 5 to 8% of it from what you're doing on the front and the back end. So why don't we go even to shorter wavelengths like X-rays or gamma rays or things like that? It's, well, near UV still works with optical components like reflectors, like mirrors. When we start talking about things in the visible to deep UV, we can still use simple things to block it or to direct the light. As we get into deeper UV, you need different materials for your reflectors and for your lenses. And deep UV, if you've ever heard of UVC or UVC band, is deep UV, and it's actually destructive to human tissue. It's used for sterilizing hospital operating rooms, and people can't be in there at the time that it's turned on. So blocking needs to be absolute. If you talk about X-rays, it's even further along. High flux X-rays are destructive to human tissue and requires lead blocking. And gamma is just over the top. We don't have anything that can direct like a mirror or focus like a lens when it comes to gamma ray. All we can do is just put dense materials around the outside and confine the beam by clipping off the edges of it. So gamma and X and deep UV are just, they'd have obviously higher energy, higher momentum photons, but that's not the way to go. So this thing is going to be producing a lot of waste heat. How do we get rid of that waste heat? Well, pumping liquid cooling through it and then backing that up with forced air movement cooling, that's kind of be what you're going to need. So it'll take a lot of back end cooling. And like I mentioned, adding Seebeck on the back and piezoelectric on the front will also dissipate some of that waste. Here's the one that's a little strange. Amplitude clipping. So if I smack it and it generates a gravity wave, that will give me the peak up. And then the peak down, if the LED is still turned on, will generate the downward slope, but semiconductor LEDs and even lasers have a minimum switch on. So you have to put a certain voltage in before it's even going to start producing any photons out. So it kind of clips off the bottom. So you have to adjust the scale of things so you have a curve that goes up and down. Otherwise, you have to adjust your modulation where you can only modulate on the upside of the wave. But you might say, well, these really long gravity waves, the wavelength is just too long. You're not going to be able to communicate any data off of it. And as we learned from last week, it takes about 8 kilobits, 8,000 bits per second, for even highly compressed voice to be transmitted as live voice. But how do we do this if we have something that is, a light year long wavelength? Because that's even less than that. It's less than a wave per second, fractions of a wave per second. Well, we do that today. We just have multiple channels side by side, and we send them all together and encode that as what is known as a multiple link layer or a mesh. You can buy for your home. If you have bad Wi-Fi in your house, you can buy a mesh network, and it's 3 channels of Wi-Fi access point, and they work collectively together to send the signal across multiple channels. And it really improves the data rate within your house. Obviously, it's not going to go faster than your internet service provider is providing you, but these are off-the-shelf technology. But if we want to be even more efficient at sending voice, send the data, don't send the voice itself as text. That's very compressible. And then at the far end, have a computer just synthesize the voice. Much easier to do it that way. So if we had many millions of gravity wave channels, we could now send parallel data, and we could encode things like voice and video and all kinds of stuff. If you received just one of those channels and demodulated it, you wouldn't even know what you're receiving. You would have to receive a bunch of those channels together, properly synchronized and aligned, before you could start to see that there's data here. But the propagation time would still be no faster than the speed of light. Speaking of propagation delay, we encounter this in normal communications. So if you're talking with a geostationary Earth orbiting satellite, there's about 120 thousandths of a second data time to go from Earth up to the satellite, and then another 120 milliseconds to come down. Propagation delay. But they're actually off-the-shelf protocols. One of them is called Aloha, that I actually worked with back in the day, that is used for multi-channel satellite communications, where you need different stations all running simultaneous channels. Now, the stuff that's lower Earth orbit, about 500 miles up, like Starlink, it only has about a 2 millisecond up and 2 millisecond down lag. So the closer you get, the shorter the propagation delay. But if you wanted to send to the moon, it's just over 1 second. Not a lot of seconds, not minutes. But if you wanted to send to Mars, I think it's around 3 minutes. So we're not going to solve the light speed barrier. But if you want to very reliably send data through space, unaffected by cosmic events and other things, then you could modulate multiple channel gravity waves. But what about security? Since gravity waves will pass through pretty much anything that's on the receiving field of view of your gravity wave signal will be able to pick it up. Friendlies, adversaries, ETs could pick up your gravity wave signal. But just as we do for other forms of communication today, we encrypt them. We require authentication to make a connection. We use encryption to make the signal where it's not easily decoded. We could do that with gravity waves. It's just data. But how do we know what gravity wave wavelengths, frequencies we can send and receive on? You may not realize this, but when they talk about radio, you're used to like tuning things on your radio dial. The FM band has a bunch of radio stations. The radio stations are all separated at known frequency markers with known channels, and those are allocated by the US FCC and internationally by the International Telecommunications Union, because all of those transmitters have to share the electromagnetic spectrum. So you can't just transmit on whatever you want. You have to play nicely with others. So if we want to do the same thing with gravity waves, we need to start thinking now about what would be the channelization. Who would be the organization that would say what channels you can transmit on and how many, who gets what channels if you want to transmit a bunch of channels bonded together to get more data throughput. So how would we know what frequency we want to use initially for gravity waves? Well, here you go. This is a chart that across the bottom, you have increasing wavelength. And then each of those blue sort of objects up there with the vertical lines give you the band spread of each of these objects as their cosmic emissions in nature. So if you said, well, I'd like to transmit at a particular gravity wave wavelength, where would I not interfere or be interfered with by other things that are producing gravity waves? Well, they're producing gravity waves pretty much at all the wavelengths that are out there. So all you can do is try and pick a quiet spot on the dial. Now, pick something like, I don't know, above pulsars, but below stellar mass black holes. There's not a lot of them. So you could pick a gravity wave wavelength that was greater than the Earth's diameter, but smaller than the Earth-Sun distance. And that would give you a kind of a free channel to start transmitting your gravity waves on. And all you would need is a little above and a little below, and now you can have multiple channels there. So you'd start somewhere in here. And I said, well, this is a lot of gobbledygook here, but I said, how did Marconi do this? When Marconi was first starting to do radio transmissions in the electromagnetic spectrum, how did he know what frequency to transmit on? Turns out it was just convenient parts. Like what he built would transmit at about 850 kilohertz or 350 meters for those ham types, 350 meter band. Well, he just got lucky, picked something that didn't have a lot of conflicts in it. But over time, 850 kilohertz turned out to be, that's something that the FCC allocates for other purposes nowadays. So Marconi had to stop transmitting on that, had to give it up. Well, obviously he gave it up when he found he could get better by using higher frequencies, shorter wavelengths, more energy transfer. But we'd have to do the same thing with gravity waves. We might pick a good, easy one to start with, and then realize, well, as the international folks got involved and we started having government institutions allocate all these things, may have to have your frequency told to you and you stay within your guidelines when you're transmitting. Here's an insider. In the US, infrared, UV, and X-ray are controlled by the US Food and Drug Administration, not the FCC. Everything else is controlled by the FCC. But visible light, street lights and things like that, those are all still in the electromagnetic spectrum. But because they affect us visually, they're not controlled by government entities at the federal level. They're controlled by local governments as light pollution. So if you have light pollution ordinances, that's actually the government dictating what frequencies and amplitudes you'll use for certain emissions. So I picked, maybe we'll start with a wavelength at about a half an astronomical unit. That's half the distance from the Earth to the sun at a frequency of about 0.06 hertz, or about 4 minutes per wave peak. That'll avoid the interference from pulsars and from the sun, while still keeping the propagation delay at about 4 minutes. Don't have to wait long for a signal to turn around. So in summary, gravitational wave background exists. It's been recognized. They need to create new ways to generate low frequency gravity waves and create a carrier for that. And then once we have a controllable carrier, you can produce modulated gravity waves and put some data on it, put some signal on it. Turns out that how you produce it is more a matter of pressure rather than it is force. Don't just throw photons at it. You want to actually adjust the pressure of the photons. You want to be able to modulate multiple side-by-side channels to communicate more data. in the same time frame, and that we've got an initial modulated gravity wavelength of about half an AU, 6.06 hertz, about 4 minutes. That will give us a single frequency modulated channel. And then you can wait for the worldwide organizations to go, well, now that you're transmitting in gravity waves, everybody wants to do it, and we have to start, allocating channels. And once we can communicate in gravity waves, and there's no more limits on how far a good signal will go, and it will go through pretty much anything, and maybe who will start listening. Lots of links, gravity waves, mass dampers. Those are in buildings. The electromagnetic launch systems of aircraft carriers, Newton's cradle, and then all the different things associated with photons coming out of devices, irradiance, luminous flux, what a lumen is, how that translates to the SI unit of a candela, and then how the photons are dispersed. That's by steradians. And there's a video on YouTube. How do you calculate the number of photons per second produced by a certain wattage light bulb? It doesn't get down into the minutiae of all the different ways that you can come up with less than what you think, but it's something interesting to watch the math of it. And then if you want the specs for a royal blue 100-watt LED, you can go buy those on Amazon. I think it's about $10. And then for the distinction between force and pressure, there's a StarTalk video on that. And then if you want to know about the various ways of modulating information onto a carrier, there's that. How to have multiple channels collectively sending data parallel. And then there's mesh networking, if you want to know about that. And then how the radio spectrum is allocated, the rules for that. Comments, questions, counter opinion?
Yes, I have one.
Yes.
Well, I have several, let's say, but I will only ask one. My one question that I find, maybe I missed it, but whenever we start something new, like they thought that and we use this a lot of times, we talk about the car and how wonderful it was when we started out and they developed all the cars. And now we've gone through many generations of seeing some of the bad side effects and trying to counteract it. I was wondering when I was listening to this presentation, it's not on my mind throughout the whole thing, but I'm thinking, have they looked at some of the negative effects of going into this area of a new type of generating and using these waves? And that's my question. Okay, thank you.
Well, the particular thing that we would be modulating, gravity waves, they exist all around us all the time, and we don't have any ill effects from them. There's no destructive effects on our infrastructure. There's no ill effects on our biology. So, yeah, I think unlike combustion in vehicles and such, there were ill effects noticed from the beginning, but it disperses into the air and nobody pays much attention to it until you have billions of those things emitting it. I think the same thing might hold true for current electromagnetic spectrum communications. People are always concerned about, if I hold my cell phone up to my head, am I going to get brain cancer? Well, that's a matter of the energy produced and the amount of energy the tissues can take over time and exposure levels. But that's because electromagnetic radiation at certain wavelengths and energies is what is known as ionizing. In other words, the energy can impact an atom and the atom will lose an electron. That's ionizing radiation. Gravity waves do not appear to be ionizing radiation because otherwise they would be making things glow all around us. And they don't seem to be doing that. I would say if we wanted to pick something that would be even better at communication than modulating gravity waves. That would be if we could modulate neutrinos. But so far, our ability to generate neutrinos requires a lot of nasty radioactive emitters, particle accelerators, and things like that, which, yep, they can generate neutrinos, but they also generate a lot of radioactive stuff. So I would say gravity waves are better at communication through deep space, and they, at least as far as we know now, are far less harmful than using the electromagnetic spectrum to do the same thing.
So I would be like trying to understand how would you generate the gravitational wave if light doesn't affect space-time, but light gets affected by space-time. So if you have something heavy, you can change the direction of the light because that mass is changing space-time. What I don't understand, how something like, most of the lights that we use to produce some light pressure, they produce micronewtons of force, sometimes even millinewtons or nanonewtons. So I don't think they would be able to generate enough energy to make an object vibrate enough to produce some gravitational wave. And I think that object needs to be intrinsically massive to have its natural bending. And then when you vibrate the object, then you will be able to modulate that gravitational wave.
And I think if we realize that the only way to generate gravity waves is the way that nature does it, then yeah, you'd be correct. But if I can transfer momentum to a reflector such that an 88-pound mirror can move nanometers, I've created a gravity wave by that 88-pound mirror moving. Now,
Okay.
granted, it's not huge, but I used light to do that. So if I can move a mass, even if it's a small distance, I've literally moved that mass through space-time. So it's not the photons themselves that are generating the gravity wave. It's the abrupt deceleration of them by the reflector and their momentum transferring into the reflector and moving it. Now, it doesn't have to move it a long distance. The best way to think of it is your contemporary cell phone. How big a speaker does it have? It's
Tiny.
minuscule. How do they move the speaker cone such that you can hear the volume? Because it's no longer a speaker cone. It's a flat piece of metallized plastic that they literally invert a piezoelectric material. So they put energy into the piezoelectric material, which transfers momentum to this metallized piece of plastic. And that vibration is what you're hearing as an acoustic wave. So this is,
vibrating in the air, transferring that momentum to the air and the air to the air.
You're taking the photons and allowing them to smack into a mirror. And the fact that it's smacking into this mirrored surface creates a resonance in the surface if you hit it often enough.
Okay.
So much like you
But
don't.
that mirror would need to be a massive mirror.
No, it doesn't. No more so than if you look at old stereo systems, they had, 24-inch speakers. They don't have 24-inch speakers anymore. How did they do that? They changed the way in which they generated the acoustic wave. It's still vibrational, but it's now tiny. You go buy speakers for your home computer that are 20-watt speakers, and they're 3 inches in diameter. And you get huge sound out of them. How is that possible? Because they're no longer paper magnetic accelerated cone pushing the airwaves. They're plastic. They're piezoelectrics oscillating it.
In the case of a mechanical wave, but I don't understand how would that, if it's not a massive object, I don't think it would bend space-time to generate a gravitational wave.
There's a presumption that space-time is durable, and therefore you need a lot of force to have any effect whatsoever. And I think it's the same as how big a speaker do I need to make it audible when you're close to it? It doesn't need to be a very big speaker.
Mhm.
Same sort of thing. If I want to produce a modulated gravity wave that's only going to go from here to Louisiana, how big a gravity wave do I need to generate? Maybe a lot less than if asked to cross the galaxy.
But you know that the gravitational waves, they move forever, right? So even if
Nothing
it's
stops
very
them.
tiny modulation, like let's say is a nano wavelength,
Yeah.
it would be traveling forever.
Yes. Is there a problem with that?
No,
It's an unstoppable signal. We like that.
yeah. I just don't understand how you would generate it if there is no mass involved.
No, there is mass involved. It's just that it's not galactic sized mass. It's not quasars or black holes or things like that, but you're not looking for that scale of effect. Start small. See if you can.
Well, and then it's like even the pressure that you're implying using photons, those are like the pressure, the light, it's like less than nanonewtons.
The efficiency of photon generation of contemporary LEDs is much higher than it used to be. Back when ion propulsion first came out, everybody scoffed at it and said, it'll never be useful because it produces such little thrust. And that's true.
Micronewton.
Yeah, micronewtons. But we developed spacecraft and orbital satellites that all use ion propulsion because it's
Yeah, but they're in space and they're not confronting with air pressure or nor gravity,
well,
not stronger gravity.
if my gravity wave generator generates any gravity waves whatsoever, then
Okay,
it won't matter what the Earth's gravitational field is.
sure.
So start small, prove the
Okay.
concept. Then you can
But
start
I don't
building.
think we would be able to, because we need mass, like we are bending space-time around us
Yes,
already,
yes.
but it is so little that it's not detectable.
Um, it's
Remember that it took
it's not
like
the
100 years for us to detect the collision of black holes.
That's because we knew something massive was going to occur, so we designed to only look for things that are massive. We don't have the technology at the moment to detect extremely long wavelength gravity waves directly. That's why we have to look at them in the ripple of the cosmic microwave background. So indirectly detection is where we usually wind up. If you look at the other approach, which is indirect emission, we now have MEMS parts, micro electromechanical systems, where we produce things that vibrate, essentially a quartz diving board on the end of open space at the nanoscale. And then we produce electromagnetic field around that. And this quartz finger moves up and down very rapidly. And we can generate output from that. We can generate radio waves from it. We can even generate light waves from it. So as we improve the science, things get smaller. For example,
Yeah, that it's like the other thing is that if it's so light and then let's say the detector's close by, if the detector is in the same uh space-time as the emitter, that wavelength that's being transmitted by the the emitter, it's gonna be moving the detector too. So they will be like in sync, and that would not be noticeable if the detector is small. You still need a ginormous detector.
The detector needs to be within sort of line of sight of the emitter because it's a planar transmission. But it need not be nearby. So it could be, as you said,
Farther away.
these will
But I mean,
transfer.
it could be, but it will be in the same space time as it's our reality. We are only at, and then so let's say LIGO or VIRGO, they can notice the difference in space time of a fraction of, you know,
Gra- uh, the,
param.
the lowest frequency gravity wave that the interferometry style with gravity wave detectors is 5 hertz. They can't detect any frequency lower than 5 hertz.
Yeah. So
So
it's kind of, they're very tiny.
yeah, you would need to make a detector that matches your transmitter.
And it
Think
will be still an L detector because it would, that generation
detector.
would shorten one side and longer the other side.
Yeah, you would not use a laser interferometer to detect it. You would have to detect it through a different means.
Okay, yeah.
Think about,
That's a conjecture exercise. That's the gunking experiment.
yes, and they said that about ion propulsion. Come back later.
Yeah, okay.
Um, think about the wavelength of the radio signal that your mobile phone uses. 900 megahertz.
It's
If
microwave.
the antenna was naturally resonating, how big would the antenna need to be for your cell phone?
Centimeters because it's a microwave.
It is microwave, but it's 900 megahertz. What size is the antenna inside your cell phone?
I don't know.
It's extremely small. It's smaller than a postage stamp. It's called
Oh
a
yeah, okay.
it's called a fractal antenna because we developed
Like
digital
even if
signal
you
processing
stretch it,
technology.
it would be what? Less than maybe 2 or 3 centimeters if you
Yeah,
stretch it.
yeah, but it's much smaller than that because we use fractal antennas. And then we use a digital signal processor to literally pluck out of pieces of the received signal the wave. And then we reassemble the wave in real time.
That would be find the wave to detect like the smaller one would be very clever.
Well,
But
humans are no,
well, but like from the beginning, I wanted just to see if we could generate something
yeah,
that could be detectable. And that would be like very curious to
you already
do that.
are.
Like move like something massive, like a rocking ball, and see if LIGO could detect it.
We are already doing that. Whenever one of the modern US super aircraft carriers launches an aircraft, they're electromagnetic launchers. They take a aircraft fully laden with fuel and armament that weighs lots of tons, and they accelerate it from 0 to 170 miles an hour in like 2 seconds. That generates a gravity wave. And then when the aircraft leaves the end of the carrier and the shuttle comes to an abrupt stop and then pulls back, that generates another gravity wave. I don't know if
Can they detect it on LIGO?
I don't know if LIGO has the ability to detect that. I don't know if we've got a gravity wave detector that can detect that. But as I indicated in the last presentation, I did exchange email with a principal scientist who's detecting Earth mass gravity waves. In other words, gravity waves from ocean movement and gravity waves from atmospheric wave movements, from wave fronts in the atmosphere. And they can detect those, but they're unable to detect the inertial mass dampeners at the top of tall buildings, the big
Okay.
multi-ton concrete things that just sort of slide around to dampen the wind pressure on the building. He said they're not sensitive enough to detect that, which means that either the amplitude is too small or the frequency is less than 5 hertz. But he just, nope, we can't detect that. So yes, we need to create new and different gravity wave detectors, and we need to create gravity wave carrier.
That's why I want like 2 ginormous wrecking balls inside of a vacuum tube and just bang and see if they can.
Well, it wouldn't be a vacuum tube because they swing on an arc.
Yeah, well, a vacuum building,
Yeah.
a evacuated building.
What equipment are they using to detect those atmospheric waves and things like that are much smaller than 2 black holes coming together?
They're using orbiting satellites to detect it as a matter of Earth's magnetic field basically squeezing and pulling due to the mass of ocean wave fronts moving and due to the mass of giant atmospheric waves moving. So you can look up.
What was the detectors who detected the oceans moving?
It's satellite based. It's magnetic field based. But if you can Google terrestrial gravity waves, and you can find their scientific project.
Yeah, we know that we can detect some gravitational fields, not waves. If you travel 2 satellites around the Earth or around the Moon, you can see where, areas that are more massive and the satellites come close together.
Oh, yeah.
The areas that are less massive, the satellites move away. So you can detect you can map a whole planet, the gravitational field of the planet.
Mm-hmm.
So you can notice some stuff with satellites because they change position.
I think of it as, imagine we're just starting to explore radio communication. We're doing things in amplitude modulation on a certain frequency. If there was somebody transmitting a complex signal and we had no radio to receive it and demodulate it, they could be transmitted for hundreds of years. We wouldn't even know they're there. It's like, I got an
didn't exist.
What's this I hear about people talking on FM radio? I can't detect that. Same thing with gravity waves. Gravity waves currently, with the interferometers and the pulsar timing arrays, they can only detect certain amplitudes and wavelengths. If it's outside their observatory's sensing ability, things could be happening all the time they never even hear.
That was another detection. I think the first one that I read long time ago, it was like putting satellites outside of the Earth and try to observe the frame dragging of the Earth in space-time. That was, I think, the first detection.
Yeah, it takes 2 satellites to do that. You're literally keeping the distance between the 2 satellites to a very high accuracy, and as you go through the frame drag of gravity, it pulls them apart and pushes them together. And now you can measure, using radio communications via laser, the distance between the 2 satellites down to probably nanometers.
Yeah, that's interesting. That's really interesting. If we ever could modulate it, that would be amazing.
Yeah, well, it's creating a gravity wave is probably the first step. And
yes,
then, now that you can create it, how would you, under control, create that gravity wave of a reliable, continuous wavelength so that you could modulate it and put data on it?
Wrecking balls.
Well, I think if we start with, let's broaden our gravity wave detectors so we can detect a wider range of gravity wave wavelengths and frequencies and amplitudes. If we do that first, we're probably going to find that there's a lot more gravity waves going on that we just don't have a radio to listen to.
Everywhere.
Yeah. Okay.
Are we still recording?
I was about to say, anything else before we stop recording? Hearing nothing.